Greetings, my name is Moses Moshabe, and I'm here to take you through the model selection and what kind of models we selected, how they learn, and what their architecture looks like. Let's dive straight into it. So, I'll start off with the model architecture, and of course, we selected the graph convolutional network model, and I'll just pass you through what really a graph convolutional network is. So, if you know about graphs, they're just mathematical structures that have nodes and edges, and nodes are connected via edges, right? And this just represents the relationship between the nodes. And so, here, the graph convolutional network model is actually a type under convolutional neural networks, and the convolutional neural networks deals with image recognition, but we shall not go into that. We have things to discuss here. So if you zoom in a little bit uh, on the picture, you see that we start with input is actually inputting traffic data into the algorithm. And if I can just picture for you what our traffic data looks like, it has rows and columns. It is in a tabular format. And so every row represents a node for our graphical convolutional network, right? Every row represents a node. So you input in these data points, and the algorithm interprets this as nodes, right? So inputting these records into the algorithm, that's the first stage. And then we have the input projection, but I want you to highlight the ray LU, which represents the rectifier linear unit. And this is all about this unit here. It introduces or imposes non-collinearity in the algorithm. Why? Because our data literally is complex data, and if an algorithm is to learn complex patterns in the data, it needs to have non-collinearity in the data. For example, I'll give an example of the curves. We used to plot curves back then, and uh, where there is no linearity in the data, we used to plot curves. So this is what it does. If the data is complex enough, the curve cannot be straight. That is a simple line. But this is not a simple line because patterns keep changing, and then there is no straight line in the data. So this introduces that to allow the algorithm learn complex patterns. Then if we go to the next rectangle, we have the residual block 1. If you look at it, we start with the GCN convolve, right? And the basic idea is message passing here. The traditional neural networks, for example, the MLPs, have nodes independent of one another, so there is no message passing. The node doesn't know about its surrounding at all. So we introduce this graphical convolutional network, or uh, this model. The nodes have information from around around the neighboring nodes, right? So message passing allows this node to receive information from around, right? It's like making a decision, but you have friends in your life that influence the decision you make, right? They give you advice that this is not right, that is right. So this is it. That's the analogy I can give here. So the node makes informed decision or predictions because it has information or advice from around. So then we have batch normalization. Now normalization comes in because we have features that have different units. So normalization comes in to make a scale for us to put on our features so that they don't over dominate. The ones that have bigger values don't dominate features that don't have big values. So this would mean that we don't overlook certain features because they have smaller values. Some features are not important, but they have bigger values. You get the point. So the model might focus on features that are not important because of the values they have, the magnitude. So that's what batch normalization does here. Then we have we repeat this process. You see that block residual block 1 is similar to residual block 2 and residual block 3 because the process is repeated. So I want to highlight certain things. I said message passing is very important, and that is how the model learns, right? The nodes learn downwards, and you have to note that prediction happens downwards, but learning comes from downwards upwards, right? From down upwards, right? So forward passing forward pass information flow, that is what it does. Information is passed on downwards to the depth of the node, but then learning happens coming from through a process called back propagation, right? To learn. So prediction and loss calculation is about attaching weights to these things. So you see that you have made a prediction, but you need to count the loss. You need to get the actual value expected minus the the value predicted, right? Then backward pass error propagation is about calculating the error in the predictions. Then weight update is where actual learning actually happens, and that happens through backward propagation. Then we repeat these steps 300 times, something called epo ep epoch epochs. Yes, epochs. So I made my algorithm through 300 epochs, and we got an accuracy of 85%. Then about model optimization, we use the Adam optimizer, and this is a smart way of optimizing an algorithm. Why? Because it has an adaptive scaling per parameter. So there are weights attached to every parameter, right? We attach weights to every parameter. As the model learns, it gets to know which parameters are important, which features are important, and it attaches weights. So every time you go down the graph, some weights are added to parameters in case they look important. Then model auditing, we use the train test split. So to know how our model is actually working out for us, we split the data into two, the train data set and then the test data set, and that way we could audit the model and know how well it is generalizing on unseen data. Then the accuracy of the test score, of course, we had to test, and I got the percentage of 85%, which showed me that the model was really doing well with the predictions. And then parameters and hyperparameters, we have the GCN layer weights, the batch norm parameters, the input projection weights, the output layer weights. Then the hyperparameters, we have the learning rate, and of course you need to know the definitions of these parameters. Are things that the model learns as it encounters the data. Then the hyperparameters are the things we set ourselves. So the learning rate is set by ourselves, but the GCN layer weight is predetermined as the model learns, right? Yeah. And then the number of epochs, I talked about these. I set them myself, 300 epochs. That's the number of repetition. You know, the number of times the algorithm goes through the data itself, the data set. So model 2 was the long short-term memory. Now, this is a type under the recurrent neural networks, if you know those. The recurrent neural networks are simple. They are simplistic in a way. If I can explain, the recurrent neural networks learn in a way, in a way that is in this format. So in case you don't know, the recurrent neural networks are graphical as well. So a node takes in the output of the previous node as its input, and then it learns, processes the information, and then it has to output certain data. It's more like learning from the environment as well. But what is the shortcoming of the recurrent neural network is the long-term dependency problems, because as information comes in, some has to be erased. That is what we call short-term memory. Some has to be erased, and that is forgotten. So some important context is forgotten. So the long short-term memory algorithm comes in to solve this. It introduces what we call the state. If you look closely at that diagram, you can see something, the state there at this point. This is called the state. So the input comes in, but it stores state of the previous node. So I'll give an example of our traffic data. For example, in the morning hours, we have high peaks of traffic, right? Traffic is building up. So input comes in, and then the state is stored. So for example, morning hours, traffic is building up. So it processes the data and inputs a prediction out here, right? So it has context. It is like contextualizing what we have, and this is only done to keep information that is important. So the state is made up of three parts: the forget get, the input get, and the output get. The forget get says what information is not relevant in the state, what information needs to be forgotten, right? And it keeps relevant information, what information will be useful. For example, context information, like uh, in the morning hours, traffic is building up, right? So we keep that information for future use. Then the input get decides what information needs to be kept. Then the output get decides what information needs to get output, right? So that is the introduction to rectify the recurrent neural network. So how the model learns is sequencing input. So you first input a couple of time steps, and the model looks at them before it makes a decision. Then it undergoes what we call the LSTM processing. So each layer is responsible to learn here. And then the attention is about assigning weights. You assign weights to every step there. And then feature extraction, this is where you choose out the important features that influence prediction, and then you classify, you do what we call classification on the last step here. So there are four classes, either high or heavy traffic, and then moderate, normal. Yes, those are the predictions. Then we have model optimization, where we use the Adam W, which deals with adaptive learning rate, right? We talked about this in the previous model. And then of course there's faster convergence. here the model learns a bit faster because there is high convergence when it comes to Adam W optimizer. Then model audit, we use performance metrics and then the confusion matrix. Of course, performance matrix is about how the model predicts. You understand how the model predicts and how correct it predicts the output of the matter. So that is it. We used the LSTM and the GCN as the graph convolutional network. Thank you so much for listening. My name is Moshawe Moses. Good evening.